Okay, hello everybody. I see a lot of people in the chat room. Can you let me know if you can hear? So I see Constance, Nicholas, Justine, Colleen, Ashley, Nicole, and Eve. Good. All right. Is it too loud? Should I put it down a little bit? Too loud or okay? Okay. Okay, because I remember last week it was too loud. Okay, so we're going to go ahead and get started. We're going to do sections 5.8 and 9.3, and these are the last two in Unit 1. So remember, next week your assignments are going to be on Tuesday, due on Tuesday, because of the Memorial Day holiday. I pushed them from Monday to Tuesday, and you'll be finishing up Unit 1. So you'll have 2 homeworks due, and then also the quiz. And you also have your discussion topic due also next Tuesday. Okay, so 5.8 and 9.3. 5.8 is the Fibonacci sequence, and we're going to learn about the Fibonacci sequence and also the golden ratio. So the sequence is named after Leonardo of Pisa, who is also known as Fibonacci. And he was one of the most distinguished mathematicians from the Middle Ages. And he's also credited with introducing the Hindu-Arabic numeral system into Europe. So he was a kind of famous guy. So here's what the sequence looks like. And in this sequence, the first 2 entries are 1s. And then the pattern that we notice here is each subsequent number is the sum of the prior 2. So for instance, to get to 2, we do 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so forth. And so the sum continues on in the same format. So every number is the sum of the prior 2 numbers in the sequence, Fibonacci sequence. And your discussion this week is about this, isn't it? I asked you to post about either the Fibonacci or the golden ratio. So in the middle of the 19th century, mathematicians found strong similarities between this sequence and many things in nature. The seed arrangements of petals on plants, some of you posted about that. The pine cones and the pineapples, I know a few of you picked that as your example. Now, what you're going to have for homework, there's not a whole lot I can ask you in here. So some of the problems ask you whether a sequence is a Fibonacci type of sequence. And if it is, then they want you to list the next numbers in the sequence. Let's take a look at an example. So here's one here. So if it's a Fibonacci type of a sequence, it means that each term is going to be the sum of the prior 2. So we take a look here. 4 plus 11 gives us 15. But 11 plus 15 doesn't give us 30, does it? So therefore, this is not a Fibonacci type of sequence. So we can't answer the question of what's coming next because it's not following that pattern. I don't know if I gave you another one. I think I did. Yeah. How about this one? Anybody want to try this one? Does this look like a Fibonacci type of a sequence? Remember the rule that we use. This plus this has to equal the next entry. So what do you think on this one? And if it is, what are the next 2 numbers? Yeah, it is. What are the next 2 numbers in the sequence? Anybody want to try on this one? Yep, we get a 15 and then we get a 25. Excellent. Yep. Okay, so that's really about all we can ask you in here, honestly. And then the golden ratio. Now the golden ratio is approximated by this fraction, the square root of 5 plus 1 over 2. And what's interesting about this is it's the value that you get when you make the ratio of the n plus first to the nth term in the Fibonacci sequence. Let's just go back for a second to my Fibonacci slide. So the golden ratio comes from taking the ratio of 21 over 13, 13 over 8, 8 over 5, and if you keep going, the same thing's going to happen. And it comes out to be approximately 1.618. So that's something else that comes out of the Fibonacci sequence is this golden ratio, which also appears many places in nature and in the world. And the symbol for it is the Greek letter phi. So this is called the golden number or the golden ratio. And it's also used on line segments where the ratio of the whole, AB, to the larger part, AC, is equal to that same golden ratio. And also AC to CB also follows the golden ratio. So kind of interesting things that go on here. So here's what it is. It's also called the golden proportion or divine proportion. It's about 1.618. And again, remember, it comes from the Fibonacci sequence, where you take the ratio of the subsequent terms, and as you get larger and larger in the sequence, it comes closer and closer and closer to this number here, which is approximately 1.618. And it appears in the pyramids, golden ratio in architecture, the ratio of any side of the square base to the altitude, so side of the square base to the altitude is about 1.611. We also see it in the human body. So if you take the ratio of the height of the head to the distance from the neck to the navel, also from the feet to the knees is 1 unit, and then from the knees to the navel again is another 1.618. There's also golden rectangles, where we look at the length of A plus B over A is equal to A over B, and is also equal to, if it's a golden rectangle now, then it's going to be equal to 1.618. Not every rectangle is going to follow that. And the smaller rectangle here is also a golden rectangle. You see it in seashells, the spiral curve in these chambered shells as the golden rectangles in the Parthenon. And then also in many Greek statues and vases and so forth, they show the golden ratio in their proportions. In artwork, I know some of you posted about some famous paintings that had golden rectangles in them. Fibonacci sequence appears in numbers. Any of you that study music, an octave on a keyboard has 13 keys, 8 white and 5 black, and those are both Fibonacci numbers. 8 and 13 and 5, those are the Fibonacci, remember, in the sequence, 5, 8, 13. Also in different music, Gregorian chants and the works of many composers. So the question always is, why does this appear so many places? And we really don't know, because a lot of this showed up well before people were measuring things. But it appears that there's a nice harmony that the golden ratio creates that's pleasing to the ear and to the eye. So we really don't know why. But it's interesting to think about it because it's been there for so long. And then a German physicist, Gustav Fechner, tried to determine which dimensions were most pleasing, and he found out that people do unconsciously favor the golden dimensions when they buy things like greeting cards, mirrors, and other rectangular objects. You might want to measure some things in your house and see if like a picture frame, if the height to the length or the height to the width follows the golden ratio. Okay, now again in the homework, I don't have a whole lot to ask you, so one of the kinds of questions you'll see is determine if the item described is designed in accordance with the golden ratio. So they'll give you a width and a length, and you're just going to form the ratio and see whether or not it's a golden rectangle or follows the golden ratio. And in this case, if you take the proportion, 35.54 to 19, the ratio comes out to be 1.87, which is not the golden ratio. I should mention, when you're doing the homework, sometimes it makes the larger one the width and the smaller one the length. So just do the ratio in the way that we see here, larger number in the numerator, smaller in the denominator. All right, and then just a little example to finish up with. Question from Nicole. Yes, 1.618, yeah. Approximately. It might be a little off. It might be 1.617, 1.619, but you want it to be pretty darn close to 1.61 something. So the one we just did that was 1.87 was way off. Yep, this is it. This is all about it. So let's take a look at this one. A line segment is divided into two segments such that the ratio of the long to the short is equivalent to the golden ratio. If the length of the whole string is 8 inches, what's the length of the larger piece? So I've got a picture coming up here. Here's the picture. So the whole thing here is 8 inches, and we want to know what is the length of the longer piece. So we want to know the length of AC, and we know that it's following the golden ratio. So we know that the length of AB, the longer one, which is 8 inches, to AC is approximately 1.618. And so since I know AB, I can solve for AC, because I told you the length of the whole string was 8 inches. And so if you go ahead and solve for AC, isolate that by itself, you'll come out with AC is about 4.94. And what's nice on this problem is you go and check now. So take 4.94, divide by, take 8 and divide by 4.94, and you should come out with approximately 1.618. And you can also check the shorter part. So the shorter part is 3.06. Now remember, this to this should also be. How did I get it? Okay, let's go back. Did you understand this part here? This makes sense? Okay, so I want to solve for AC. So what do I need to do? I need to get AC by itself on one side in the numerator. So if I multiply both sides by AC, I'll go ahead and type it down here. Multiply both sides by AC, I'm going to get A8 equals 1.618 times, AC. So all I did here was, let me see if I can just jot it on here with the pen. So what I did was, trying to get my red pen so you can see it better. There we go. Doesn't want to keep the red. Red. Well, it's not cooperating, so we're going to have to go with blue. I'm trying to get you red. It looks easier. So if I multiply both sides here by AC, what happens on the left side is AC cancels. And then I'm left with 8 equals 1.618 times AC. Now I'm not done yet, right? Because I need AC by itself. So what am I going to do? I'm going to divide both sides by, let me type it. It's easier if I type it. I'm going to divide both sides by 1.618. And that's, darn. 1.618. And that's going to equal AC. Alright, so in your calculator, if you take 8 and divide by 1.618, you will get 4.94. Make sense? Okay, good. Okay, so now the other thing we can do is, if you remember when we set this up before, we said the ratio of the larger segment to the smaller segment would also be the golden ratio. So if I go ahead and I measure, this whole thing is 8. We just found this was 4.94 here. And then if I subtract 4.94 from 8, I get 3.06. 3.06. Now let's check that ratio, because that should also be the golden ratio. And it is. And again, it's not going to necessarily be exactly 1.618 because we round it off, but it's pretty darn close. So the ratio of 8 to 4.94 is 1.618. And in addition, the ratio of 4.94 to 3.06 is also the golden ratio. So kind of interesting repetition of patterns again. Okay, Justine has a question. Well, are you rounding off, or you're getting exactly 1.7? Keep a lot of decimals, because if you're rounding off, you're not going to get anything that, you're going to get it pretty darn close like this, or you're going to get something like 1.8 like we had before. Okay, I don't think they're going to trick you up like that. It's going to be like 1.614 or 1.615, somewhere in that range. But if you get 1.8, that's not it. Okay, so that's 5.8. Not a lot of problems I can give you in there, so I don't think you'll have any trouble with it. I want to spend a little more time on the modular arithmetic. And this is also called clock arithmetic, because a lot of this has to do with working on a clock. Now, this is just like changing bases. If you remember back when we did our change of bases, if we have a set of elements from 0 to 11, remember if we were working in a base 12 system, these would be the symbols we would use. But when we talk about arithmetic, clock arithmetic, this could actually be the months of the year, for instance. And we call it a modulo 12 or a mod 12 system. So a modulo system consists of the m elements from 0 to m minus 1, just like you had when you did your bases back in section 4.3. We had base 8, we use the symbol 0 to 7. Modular systems do the same thing. And we're going to look at how to do some calculations. So here's a little picture. And you can actually add. We're not going to do a whole lot with adding and subtracting, but you can also add in here. But here's the days of the week. So this would be a modulo 7 system, because there's 7 days in the week. So if I go through the days of the week, when I get to the 6th day and I get to the 7th, if I start here with 0, 1, 2, 3, 4, 5, 6. Now when I get to the 7th day, I'm actually going back to 0 again, just like we did when we changed our bases. And so what you can do with this is work out problems like this one. where you want to work ahead or back in time and see what day of the week it is or what month of the year, that kind of thing. So let's take a problem. Assume Sunday is represented by the day 0, like we just had. Monday is 1 and so forth. If today is Thursday, which is day 4, determine the day of the week it will be in the specified number of days. And we're going to assume there's no leap years. So where are we going to be in 43 days? Now you could pull up a calendar and do this calculation on the calendar, but you can actually use modular arithmetic. This is a modular 7 system, 7 days of the week. So take 43 and divide by 7, just like you did when you change bases. And I get 6 remainder 1, which we write like this in the modular system. The remainder goes in front, and the remainder has to be less than the modulus, and then we write the modulus that we're working in. So this 1 here tells me it's 1 additional day later in the week. So it's going to be 43 days will be 1 day past the current position, which means it will be a Friday. Let's try another one. Where will it be in 3 years? All right, we're working on a modular 7 system, so I need to get from years to days of the week. So 365 days in a year multiplied by 3 gives me 1,095 days. So I'm going to do the same thing here. I'm going to divide by the value of the modulus, which is the 7 days of the week. So if I divide by 7, I get 156 remainder 3, which we write like this in our little shorthand. So what day of the week is it going to be? Anybody want to try that? Today is Thursday, and we're going to move ahead by 3 days. So what day of the week will it be in 3 years? Anybody want to try? Yep, Sunday. Excellent. It will be Sunday. Yep. I think I have one more on this one. Oh no, I've got ones on months. Okay, so that was on days. Now let's go to months. 12 months in the year. And if it's currently October, determine the month it will be in the specified number of months. Okay, so this is a modular 12 system. So in 73 months, where will we be? Take 73 and divide by 12. So we get 6 remainder 1. So if it's currently October, in 73 months, what month will it be? Anybody want to try? We're going to move ahead by 1 month, so it's going to be... Anybody want to try? Yep, November. Good, Justine. It'll be November. Absolutely. Let's try another one. 4 years and 8 months. Justine has a question. I'm going to wait for a minute. Oh, you're always going to have a remainder. If you don't have a remainder, then you're going to be on the same position. So if your remainder is 0 here, if it was 0, let's say it was 72 months, it would be 6 remainder 0, you would still be on October. So the remainder part is what tells you the position in the modulus rather. So you really don't need to round, actually. You want to keep that remainder, because that's going to tell you your position. Okay, but all right, so see, now you got to get rid of the decimal part of it. So take the 6. 6 times 12 is 72. It's a great question. So you do the division, and you got 6 with this decimal. So take the integer part. 6 times 12 equals 72, and then subtract from the number you were dividing into to get a 1. So you see how I got the 1? Okay, yep. Okay, let's do another. Okay, let's do this one. 4 years and 8 months. So again, I'm going to convert to months. So 56 months, and I'm going to divide by 12. So again, notice what I did. 12 goes into 56 4 times. So let me type it over here. 4 times 12 equals 48. Subtract from 56 to get the 8. Okay, so if we're in October now, we're going to move ahead 8 positions. So what month will it be moving forward 8 positions? June. Excellent. Very good. Yeah, these are kind of fun, actually. Okay, now let's do one with Dusty. Dusty is working at a restaurant, and his work schedule is he works for 6 days, and then he gets 2 days off. If today is the 3rd day he's been working, determine if he'll be working in 60 days. Okay, so the first thing you have to think about is what kind of a modulus, what kind of a pattern does he have? 6 plus 2 means modulus 8. Okay, Okay, so it's got 8-day cycles. And I actually think, I thought I had a picture. So he's got, let me see. Yeah, let me just go type it up here. I'm going to have it on the next slide, but basically I like to kind of type it out. So he's got work, 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 whoops, work, 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 1, 2, 3, 4, 5, 6, and then he's off, and then he's off. I like that little picture to help me figure out where I'm at. So he works for 6 days, and then he's off for 2 days. And right now, today is the 3rd day he's been working, 1, 2, 3. So he's right here in his cycle. Okay, and we want to know where is he going to be in 60 days. So I'm going to take 60 and divide by 8, just like we did before. And actually, if you do it by long division, your remainder will pop out for you. So 8 times 7 is 56. The remainder is 4. So where are we? We're going to move ahead by 4 days. So is he going to be working or not working? So he's here. We move ahead 4 days. He's going to be off. Exactly. Yep. I have another picture over here, actually. This is from the book. He'll be off. Okay, let's try another one. Is he going to be working in 82 days from now? So take 82 and divide by 8. The remainder is 2. Now remember his cycle. Remember, I have a picture coming up actually, I think. Oh no, let me type it up here. So remember he had work, 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 and then he was off, and he was off. And we said he was, get my little pen, he was on, trying to get my colors to come up, right here. Okay. Let me try again. I'm trying to get my pen to come up so we can mark where I was. He was the 3rd day, right? So what's he going to be doing in 2 more days ahead? He's going to be working. Absolutely. Yep. Okay, this is a different one. Same cycle, but in the same location. We want to know if he was working 124 days in the past. In the past. So this one's a little bit harder. Okay, so let's take the 124 and divide by 8. And I get 8 with a remainder of 4. Now, I have to go backwards because I'm going in the past. See, if I was going forward, I would count ahead, but we're going backwards. And so here's where Dusty is now, and we want to go back 4 places. 1, 2, and then we go back to the beginning of the cycle, 3, 4. So he was not working 124 days ago. That was a little tougher. Going backwards. Okay, make sense on these? They're actually kind of fun, I think. So you have some like these in your homework. Yes, I do, Justine. You know me. Okay, let's talk about congruence. And sometimes we want to know if things are equal to one another. And so if things are congruent in a modulo system, that means they have the same remainder. And I'll give you some examples to show you what I mean. In any modulo system, we can develop a set of classes by pasting all the numbers with the same remainder in the class. And I think I have a picture. Here we go. So if we're working with a modulo 7 system, then all the numbers in this column are congruent, meaning if I take the number and divide by the modulus value, I get the same remainder, and the remainder's up here. So for instance, if I take 20 and I divide by 7, what do I get? 2 remainder, 6. If I take 33 and divide by 5, I get, what is that? 33 divided by 7, divided by 7 times 4, and a remainder of 5. And so that means that they're congruent. And we write them this way. Let me go back for a second. The terminology that we use is we use this equal sign with an extra bar above it. That means they're congruent. They have the same remainder. So all you're looking for is to get the same remainder. So let's work a couple problems. Determine which numbers from 0 to 6 the following numbers are congruent to in modulo 7. So all you're going to do is take the number, divide by the modulus, so take 60 and divide by 7, and we get a remainder of 4, and that becomes the answer right here. So 60 is congruent with 4, with a remainder of 4 in the modulo 7 system. That's all you have to do. And there's your answer. Let's try another one. How about 87? I'm sorry, 84. All right, so take 84 and divide by 7. We get a remainder of 0. Sometimes I told you that we get a remainder of 0, and that's okay. So the answer here is just going to be 84 is congruent. Yes, they're just the remainders. I have a couple, let me see. I think I'll put a couple extra ones in here. Yeah, I have a couple other ones, though, to show you where you have to do a little calculation, make you think a little bit. This one's pretty easy. Okay, how about this one? 412, what's it congruent to? Divide by 7, get a remainder of 6. There's your answer. Okay, so these are not really very difficult. Now, I just put a couple of problems up. I can't even remember if I signed these to you, but these are just kind of make you to think a little bit. So I want to know 3 plus 5 is equal to what? Congruent to what? So on this side, what are you going to do? You're going to simplify it. So you're going to go ahead and simplify. So 3 plus 5 is 8. And now just divide by 6. So this is congruent with 2 modulo 6 system. Not too hard. How about this one? So you're doing a little bit of arithmetic on the left side. So again, as long as the number you get over here, this is going to be a trickier one. Oh, actually, this is easy. 5 minus 2 is equal to 3. This should be the whole thing, right? So in this case, it's just 3. Pretty easy, right? Now, this one. Okay. Now you got to do a multiplication. Again, this is not bad. 5 times 8 we know is 40. So you're going to divide by 3. And you get a remainder of 1. So 5 times 8, the product is congruent to 1 modulo 3. There's your answer. Yeah, I used to give a lot more complicated ones, but I took those out. That's all you have in here. It really isn't that hard. But the interesting thing with the modulo systems is they're very close to the change of base that we looked at. That's why we put all these things together, and also a lot of patterns and history in here. So although they seem like disjointed topics, they really do flow together. All right, so that's what we have for tonight. Does anybody have questions on anything that I didn't cover? Anything that you want me to catch up on real quick before we finish up? Okay, Nicholas is good. Justine, I think you're okay, right? Eve got in. Okay, good. All right, so again, don't forget, next week your homework and test are due on Tuesday instead of Monday. And there's also a discussion. I know most of you have probably already done that. That'll also be due on Tuesday. Okay, and then next week we start a new module. I don't remember what comes next in your course, but we start Unit 2. Next week, so when we chat on Wednesday, we'll talk about Unit 2. We'll be moving forward, okay? All right, so everybody have a great week. And we'll chat again. Have a safe Memorial Day, too, if you're traveling anywhere. Have a safe holiday. And we'll chat again next Wednesday night.